Hello everyone, welcome back to question number 7 of paper 1. We are talking about the JEE Advanced 2023. This question was based on some aspirin synthesis and its applications. We can say this was touching the chemistry in everyday life as well as hydrolysis of ether and synthesis of salicylic acid and thereafter synthesis of aspirin. Also, they wanted to test about what are these non-steroidal anti-inflammatory drugs. They had touched the noradrenaline and prostaglandin, which is basically coming in the chemistry in everyday life. So they had mixed organic chemistry very, very well with the chemistry in everyday life. We are having here the most elaborate solutions possible on internet, as we used to say over and again. This was paper conducted on 4th June 2023. This was section 2. Marking scheme was +3, -1, 0. So this is the question. The reaction scheme was given where compound P was supposed to be reacting with HI, and it was told in the beginning that this was some phenyl alkyl ether, which is P. And this upon hydrolysis with HI, acidic cleavage we can say, gave some Q as an aromatic compound, and this aromatic compound Q converted into R upon reaction with these three reagents one after another, and this compound R which was generated was reacted with acetic anhydride in presence of acidic medium. Then we had got the compound number S. Now this what S compound is, about this we were asked which of these statement is true. So whether it is inhibiting noradrenaline degrading enzymes or it is inhibiting the synthesis of prostaglandin, it is a narcotic drug, this was asked, and whether this has the name ortho acetyl benzoic acid or something else. We'll see here for every single. First of all, we'll try seeing what this P, Q, R and S might be. Thereafter, we'll be seeing the reaction mechanism of every single step. Then we'll come to the discussion of these options, like what is meant by noradrenaline degrading enzymes. And when we are talking about these drugs, aspirin we have known we are calling as the analgesic and antipyretic, which is basically we will be seeing there is a classification of analgesic medicines or drugs. So we'll be then diving deeper into what are these noradrenaline, what enzymes degrade this noradrenaline, and what is prostaglandin, how analgesics are working on the basis of that. Although that's going to be more of the medical science, medicines will not go that deep. We'll remain in the domain of the organic chemistry and chemistry in everyday life as far as our NCERT is concerned. And as far as this question was asked, we should be knowing in and out what are these options related to. Moving on, we have got here the reaction sequence. So this was phenyl alkyl ether. We don't know the nature of alkyl group. That is not necessary in this question. So when this compound is being hydrolyzed by HI, we are getting the side product as RI, and we are getting compound number A as phenol. And now in this compound number A, which is phenol, actually this names which we have used, it is rather than being A, this compound was Q as per reaction sequence, and this compound C was R as per reaction sequence, and after acetylation in acidic medium, this compound was supposed to be S as per the question. So once we are getting phenol in the, because any phenolic ether we are taking, hydrolysis is going to give us phenol. We'll be seeing in detail in the next slide after this. We are just seeing the reaction sequence, what are the products. And when this phenol is undergoing this reaction, we call that Kolbe-Schmitt reaction. Followed by acidification is going to give us this compound number R, which is salicylic acid. And salicylic acid, when undergoes this is acetylation reaction, this phenolic OH will be undergoing acetylation, and that OH group is now replaced by OCOCH3. Color code will help us understand very clearly which atom or which fragment is coming from which reagents and where it is going, where it is appearing. Even over here, CO2 and sodium hydroxide are going to give you C double bond O, this part, and that acetic hydrogen lighter green color is coming from acidification in the dilute acetic medium. And in this OH, this H has come from HI, hydroiodic acid. This H is now being replaced by CH3CO group from acetic anhydride. That is how we are getting the S compound, which is your aspirin. Now we'll split these reactions in different parts, and we'll go ahead one by one. So this phenylic ether, when it's reacted with HI, we understand that oxygen over here will get protonated, so we are getting the positively charged oxygen. Now iodide, which is very good nucleophile, is going to attack. We have got now two choices. Iodide can attack onto this carbon, that is phenylic carbon, or this R. If I write this OR as over here, there is a single bond and then there is an R. Because this reaction is not going to generate very stable carbocation, and whenever we are having the situation that no stable carbocations are being generated, this reaction is going to progress by SN2 mechanism. Now when we have SN2 mechanism, we understand that less steric crowding, or where that backside attack is happening, that can be possible. Less steric crowding is preferred. And not just less steric crowding, there is also an important signature step in this, that is backside attack of the nucleophile. So the backside attack of nucleophile is not possible over here. This attack is simply not possible. Iodide has the only possibility that this can attack onto the alkyl group R, and then this bond should be broken. So phenolic group is going to be the leaving group. R group of the alkyl phenyl ether is going to be the electrophilic center. So this is the product of the electrophilic nucleophilic reaction. And this phenolic compound is going to be produced as the leaving group. And this is compound number in the reaction sequence what was initially given. This is compound number Q. So that was aryl ether hydrolysis giving us phenol. Moving on, we have got the next step, which was Kolbe-Schmitt reaction. In this Kolbe-Schmitt reaction, we are having the step number 1, this one, which is considered to be EAS reaction of PHO minus on electrophilic carbon dioxide. Basic medium ensures conversion of phenol into more nucleophilic, because when your phenol is reacting with hydroxide ion, we are getting even more nucleophilic situation over here. And this compound will be phenoxide ion will be giving us even better nucleophile, which is going to be carbon with the negative charge. And this negatively charged carbon is going to attack onto this carbonyl carbon. That gives us, this is our EAS step, where this is the nucleophile, that is electron rich, very much electron rich ring, aromatic ring, which is converting into carbon ion momentarily. And this is the electrophile. This electrophile is being attacked, and that happening, the major product is coming from the ortho attack. We can also have a possibility of the para attack as well if the ortho position was not possible. So this is the thing what we can be getting here. So this oxygen is getting a negative charge. Now this non-aromatic ring will be going for aromatization, because that is going to be more favorable intermediate, which can be leading to the final product. So this hydrogen goes on to oxygen as O minus, and this is converted into C double bond O. O minus, we can write this as momentarily as OH, but reaction medium being basic in nature, because sodium hydroxide is present, this will not survive in reaction medium. OH minus sign will pull that hydrogen back. We could have said in the beginning only that this H plus from the ortho position is being removed by OH minus and from the reaction medium. Ultimately, this is going to be the situation. Now when we do acidification, that H3O plus which is coming over there, that acidification can be giving us the carboxylic acid. And although I had represented over here that this OH is coming from the HI, the very first step it was there, but after this step, after Kolbe-Schmitt reaction, this H is most likely replaced by the H plus coming from H3O plus from the acidic medium. For example, if you would have had here D3O plus, like D2O in acidic medium, then this OH would have been replaced by OD at the same time as this carboxylic acid would have been replaced by OD. And this is the detailed mechanism of the Kolbe-Schmitt reaction. Here we need to elaborate one point, that when we are using sodium hydroxide, this is actually getting coordinated over here with this oxygen of the phenolic O minus. And this sodium ion is helping this carbon dioxide molecule get coordinated so that the ortho position of the phenolic carbon can attack onto this carbon of the carbon dioxide much more easily. And this is one of the reasons why we see in this Kolbe-Schmitt reaction that ortho product is going to be the major one, because this coordination of the electrophile with the sodium ion is made possible, which is making the approach from ortho position much more likely for this electrophilic attack rather than from the para position. And that's the reason why para position will be attacked only and only when ortho position is not at all available in this Kolbe-Schmitt reaction. So coordinating sodium as one of the key thing over here, and that gives us another important point. If you are replacing that sodium with the potassium hydroxide, these reports are very well known for the Riemann-Tiemann reaction, although similar kind of effects are known to be happening in the Kolbe-Schmitt reaction as well. So if you are using sodium hydroxide, ortho product is being favored, but when we are using potassium hydroxide, it has been found that para product is favored, because potassium being, like if this was the size of sodium, potassium being rather bigger in size may not be allowing the access to the ortho position. So say this was your oxygen, this was your sodium ion, this is your potassium ion. So this sodium ion would have not created a problem for that actually would have helped that carbon dioxide to come onto the ortho position. The potassium ion may be blocking the ortho position due to its bigger size. So in that case, the para position would have been more likely to be attacked if there was a potassium. And this is the paper which suggests that why potassium ion, which is relatively bigger, is going to give us the para substitution. And in fact, if you are replacing that potassium to tetraethyl, triethyl and methylamine, where nitrogen is containing 4 such alkyl groups, the size is becoming even bigger, and then para product may become even the major product as well. That is the explanation coming for Riemann-Tiemann reaction primarily. But because both the reactions are going to have the similar situations, we expect Kolbe-Schmitt reaction also will be going the very same way. Moving on, we are having the third step, which was conversion of this salicylic acid into the compound number R. We should be writing this as compound number R was converting it to compound number S, which is conversion of salicylic acid into aspirin. This compound number S was aspirin, which is being formed by nucleophilic acyl substitution. So what is happening? This oxygen of phenolic oxygen is basically going to attack to this acetic anhydride. Oxygen will be attacking over here. We'll be getting some tetrahedral intermediate, and then the tetrahedral intermediate is going to convert into aspirin by loss of this thing. This is oxygen, and that is the para position, ortho position containing C-double-OH group. Now the tetrahedral intermediate is not going to stable because of too much steric crowding, so this bond is going to be shifted towards oxygen, and if this bond is shifted that way, we'll be getting acetylation onto the ortho position. So that is how this O is now going to have one COCH3 group present over here. This is CH3 CO minus. That group is appearing over here, and then this O double bond C O minus CH3 will be present onto. That is going to be a leaving group. That is how this aspirin is being synthesized in this nucleophilic acyl substitution, where the nucleophilic phenolic oxygen is attacking onto the acetic anhydride, and we are getting O-acetylation possible. There would have been carboxylic acid intact. So this compound which we are getting as aspirin, we are saying that compound number S. This compound is actually named as salicylic acid derivative. So you can say this compound is either acetylsalicylic acid or orthoacetoxy-benzoic acid, or any such similar name. The name which was given us in option number D, which was orthoacetyl-benzoic acid. It is not orthoacetyl-benzoic acid. It would have been if this oxygen was missing. If this was just COCH3 and then ortho position was COOH, then it would have been that option number D, orthoacetyl-benzoic acid possible. This compound is not that way. So that was all in the reaction sequence. Moving on about the options. In the first option, they talked about this is giving us something which is like the compound number S is, which is primarily inhibiting noradrenaline degrading enzyme. What that noradrenaline is, we are saying this is basically the hormone which is a neurotransmitter, and this is belonging to catecholamine family. We can see this is OH, this is basically, we have written is the zwitterionic form of the catecholamine, and this catecholamine is the thing which is we are saying is the noradrenaline hormone. So if this was phenolic OH group over here, this is phenolic OH group, and because this OH is acidic one, this was CHOH, this is CH2 over here, and then we had NH2 over here. This was nitrogen in the beginning. Now one hydrogen from this carbon over here has appeared over here, so that becomes NH3. This is we'll say the zwitterionic form of catecholamine. This is zwitterionic form of catecholamine, where one H plus from here has moved up to here, this place, and nitrogen is becoming plus, O is becoming minus. Okay, so what is this noradrenaline? We say this is the neurotransmitter, and this belongs to catecholamine family, and this is functioning to coordinate the brain and body. This is known to mobilize the brain and body for different actions. So because if we try to look into the patterns, this is released during different processes in different amounts. And the fact is, when we are in the sleep mode, when we are sleeping, then this norepinephrine, we are using both the names norepinephrine or noradrenaline across different geographical locations. Both are basically relating to the same hormone. So this release is lowest when we are sleeping, and when we are awake, when we are doing a lot of exercise, or when we are in stress, we are in danger, then the concentration of this noradrenaline is maximum. And so we are calling it sometimes fight or flight hormone. That is, most amount of this is present when we are in such a situation. And we know that in mammals this is rapidly degraded to different metabolites, and in that metabolism, because as long as this is present in our body, this is going to increase the metabolism, so that our body get very much amount of enough energy which may be required in that particular situation. Maybe we are fighting or we are running away, then our body may be requiring huge amount of energy. This is the hormone which is going to stimulate the body to give that situation, so body is well equipped of that energy requirement. But it cannot not be remain like if it remains in our body for a long time, in the body fluids, in blood for a long time, it will be kind of draining out our energy very fast. So its decomposition is very efficient decomposition period of time is required. Our body would be aware of like we have a mechanism for how long that situation of danger or stress is there. As that situation is no longer present, our body will try to get rid of this hormone so that the drainage of energy, unnecessary drainage of energy, can be avoided. For that, the decomposition is required by different enzymes, and that such enzyme is we call as monoamine oxidase. So this monoamine oxidase is the enzyme which is responsible for the decomposition of noradrenaline. Now, how this monoamine oxidase is related with the aspirin, we can try to look into those aspects. So this is our noradrenaline, how it is decomposed in our body, and we have here some enzyme named as catechol O methyltransferase. That has when we are having this methyl group present over here in catecholamine, that is going to be transferred, and this is how this compound is. This basically this is your noradrenaline. There are different pathways possible for decomposition. We have got catechol O. So we have got basically methyl transferase here, aldehyde dehydrogenase is there. So aldehyde that means this aldehyde group will be dehydrogenated. So we'll be getting dehydrogenation means we'll be getting oxidation. So we are getting here some mandelic acid formed, and here we are having aldehyde reductase. So if aldehyde group is being reduced, we will be getting some alcoholic group produced. So depending upon different situations, there can be different modes of decomposition. Body can be getting rid of this noradrenaline during different mechanisms. And during this process, does aspirin play any role? For that, let's say we don't have any clear-cut answer. Different researchers have published different papers. I tried looking into many of those papers, but I couldn't find any conclusive evidence. Coming to NCERT, they have given in their Chemistry in Everyday Life chapter that we understand this thing they have given, that the antidepressant drugs, these are the drugs which actually are known to metabolize they inhibit the synthesis of this degradation of noradrenaline. We can understand that there is a situation when we are in danger or we are in stress, that our body is releasing a lot of this neurotransmitter, which is the noradrenaline. Consider another situation. There are some people who are having some definite mood changes, like they are feeling very low for some reason. They have got a kind of depression phase in their life or whatever may be happening to them. When that is happening, the concentration of noradrenaline in their body is already low, and even that low concentration is being degraded over a period of time by those different enzymes which we know are degrading noradrenaline. So if for these people who are feeling depressed, if we can inhibit the enzymes which degrade noradrenaline, their body can be having enough noradrenaline present which can be lifting up their mood. So these antidepressant drugs are elevating the mood by not getting rid of this noradrenaline, which is required for energy, which is required for kind of people feeling more energetic. Their body may be having energy, they may be feeling better that way. So the medicines which are used, which we have been using as antidepressants, include iproniazid and phenelgine. These are known to be inhibiting the noradrenaline degrading enzyme, and it is not the aspirin which is known to do so. So that is the first point which we are saying about the antidepressant. Now coming to the next thing, we understand that prostaglandin and the aspirin connection. Like, what is prostaglandin and how these analgesic drugs are known to work on that. This is again from NCERT that when we are talking about analgesic and antipyretic, then analgesics are those which are abolishing pain and inflammation as well related. Then we have here two kind of analgesics. Number one, non-narcotic, which means they are not habit forming, and second one is narcotic, which are, of course, their name suggests they are habit forming. So non-narcotic or non-addictive analgesics we are sometimes calling as non-steroidal anti-inflammatory drugs, that is abbreviated as NSAIDs. So aspirin is one of the very much familiar example for this, and it is told that aspirin inhibits the synthesis of chemicals known as prostaglandin, which are responsible for the pain stimulation. So whether we are having any pain in any particular region, or we are having any inflammation which is giving us the painful state, then the synthesis of prostaglandin, which makes our nervous system feel that pain, the aspirin is inhibiting the synthesis of those prostaglandins. So rather than working onto the tissues, this is basically breaking the connection of the inflammation and the brain which is feeling the pain. That is how these analgesic, which we are saying non-narcotic analgesics, are working. These are also having one side effect, we can say, or other effect, which is reducing fever as well. And this aspirin is also has one important effect, which is known, which was supposedly known to prevent platelet coagulation, although that concentration of the platelet is having some dispute recently, like how effectively it can help people get the prevention from their heart attack situation. Talking about non-steroidal anti-inflammatory drugs, we have here the analgesics and antipyretics both. Both of these are usually going side by side, and we are saying these are most widely used anti-inflammatory agents. And these NSAIDs are known to inhibit the production of prostaglandin, and these are basically a group of prostaglandins. When we are saying this thing, these are a group of compounds which are known to contribute to inflammatory responses. So basically we have got this all situation starting from arachidonic acid, and this arachidonic acid is converting into prostaglandins, and there is some enzyme which we are saying is cyclooxygenase enzyme. So sometimes we find this term called COX inhibitor, and this COX inhibitor are basically those medicines which are preventing, or any agent which is going to prevent the synthesis of the prostaglandin. And the other things here we have that thromboxane and prostacyclins. Here is the prostaglandin. So this COX-1 and COX-2, both of these are responsible for conversion of arachidonic acid into prostaglandin. This is the enzyme involved. And what aspirin does, aspirin is doing the decrease in the concentration of COX-1 and COX-2. So sometimes we call these NSAIDs as COX inhibitors, which means they inhibit the cyclooxygenase enzyme, and if that enzyme is inhibited, then the synthesis of prostaglandin will not be there, and the synthesis of prostaglandin is not there, then this is going to be having the reduction of pain or reduction of fever. This diagram over here is again suggesting that how the oral anticoagulation agents and non-steroidal agents, if they are put together, there is increased risk of bleeding. In fact, that may be a problem if you are mixing the NSAIDs and oral anticoagulants. There are people who may be requiring anticoagulant therapy side by side, so for them it should be very well taken care of, that they should not be taking NSAIDs in beyond any particular limit, otherwise it can be having very harmful effect. Okay, so NSAIDs are known to have they are known to be very much effective, and they are not having any immunosuppressive effect like any other anti-inflammatory agents can be having. So moving on, we have got the little discussion about aspirin. So this is, we have said this is an NSAID, and this is known to be also used as antiplatelet. Of late, although that is kind of under question, people are raising question against that. We have been using this as analgesic, mild to moderate pains. We are using it for, and this is anti-inflammatory and antipyretic as well. Different situations, headache are the most common occurrences, and even those different musculoskeletal pains are also there, where aspirin has been routinely used by different people. Coming to the chemistry, a little bit of that, we call this as acetylsalicylic acid, and this has been, we understand this has been used for reduction of pain inflammation. This is also anti-thrombic, which is kind of, it is known to prevent the thrombosis, which is blood clot formation. And there are certain conditions in which this aspirin is particularly found useful, which is Kawasaki disease and pericarditis. These are some situations, and also that rheumatic fever. It was also suggested that long-term use of the aspirin was helping prevent the heart attacks and ischemic strokes, as well as blood clots in the people who are at the high risk. And this is working similarly as the any other non-steroidal anti-inflammatory drugs, but it is also known to suppress the functioning of the platelets. Talking about paracetamol, we have got another very much similar analgesic and antipyretic, that is paracetamol. We call this sometimes as acetaminophen as well, which is coming from its name, that's para-acetyl. You have got this NH2. If acetyl group was not there, this was NH2 and this was OH, so this would have been para-acetyl, para-aminophenol it would have been. But when we have put this COCH3 group over here, or nitrogen, that becomes N-acetyl, and then this is para-aminophenol. We could also say this alternatively as para-N-acetyl or para-acetyl aminophenol. So we are considering phenol to be the primary group, and NH2 is the subsidiary group. On NH2 there is COCH3 group coming, one hydrogen is being lost. That is what paracetamol is. And this is Dolo 650, which we have been using in different setups when we are requiring the treatment of pain or fever as well. Again, a brief discussion of what paracetamol is used for, and again this is NSAID, non-steroidal anti-inflammatory drug, and this is used for, this is actually weaker anti-inflammatory. This is used mostly as antipyretic and analgesic. Fever and headaches, we are mostly using this. And because this is having a little bit different situation, this is known to be relatively safer with the patients with the peptic ulcer. We have seen that if we are using that aspirin along with the what we call oral anticoagulants, then there is a problem. There is too increased risk of getting the peptic ulcers. And we have got some adverse side effects where people with the hepatic damage, because that liver needs to work a lot to get rid of this paracetamol, the residual amount of whatever paracetamol is accumulating after taking the doses. So people who are having a problem in their liver, they should not be taking much of, they should be very much cautious about taking the paracetamol. Moving on to the opioid analgesic. Option D in our question was about opioid analgesic. What's the meaning of opioid analgesic? We understand this is going to be something which is derived from opium or opium related things. So in this opioid analgesic, we have got the notable names as morphine, heroin, and codeine. What they do, we are having the use of the, like, one thing is they are habit forming. So their use should be very much closely monitored, and that must be happening in the proper medical supervision. So what are the benefits? Why, if they are habit forming, why we are going behind that? Why we are allowing these things to be used in medicines? The first thing is there is a rapid onset of analgesia, moderate to severe and very severe pain. This is the most important thing. When we are having very severe pains, the opioid analgesics are going to be the ultimate possible solutions which we can be looking for. A number of other benefits of that we are having. One important is there is no effect on key organs like cardiac, renal, hepatic, and homeostatic safety. So although they are habit forming, they are having a greater advantage in the terms of management of very severe pain without affecting the key organs. Although some of these like morphine and oxycodone can be relatively inexpensive, ultimately the people who are into it, like the doctors who are looking after the medical professional, they have to take a call in which condition and how much amount they should be used, because it is just one side of the story. There are drawbacks as well. Like one of the important drawback is that this is addictive. They form addiction if this is given for a longer time. And second, and probably the most important drawback, like we should the major hurdle what is lying in the use of opioid analgesic is that this is known to obstruct airway. This brings in respiratory desperation, and a number of times these things lead to respiratory arrest. People die of asphyxia if they have taken too much of the opioid analgesic without proper medical supervision. So that was about the opioid analgesic, and here we have these opioid analgesic which we are saying they are habit forming: morphine, heroin, and codeine. And in fact, morphine and heroin, they are related. In fact, codeine is also related only. The only difference is morphine as having a phenolic and alcoholic functional group, heroin as having ester. So these two alcoholic groups are now replaced by acetyl ester, and in codeine, one of this phenolic group has been converted into methyl ether. Another alcoholic group is remaining as such. So as we are doing the substitution of OH group with some other groups, that is supposed to be associated with the change in its property, its physiology. Physiology changes a lot by the magnitude. And depending upon the requirement, we can be changing its physiology as per the need from the medical science. Maybe that is altogether different branch. We are not going into that right now. So in medical doses, and when we are saying medical doses, we mean to say under medical supervision with the proven records, what amount should be administered, that if it is given, it relieves pain and produces sleep. And if we are moving beyond that particular concentration, like for morphine, this is known to be about 75 milligram for a 70 kilogram person. If this doses is increased, that becomes lethal. That first of all produces stupor, then coma and convulsions, which may lead to death if the concentration is going beyond that. And then where we are using it, as we have seen, to manage very severe pains, we are using it. So the important cases where these opiates can be used, and they are actually used under medical supervisions, that is post-operative pain, that is after surgery, cardiac pains, pains of terminal cancer, where it is very difficult to manage the pain using whatever other concurrent therapies might be going on, and even childbirth, which is one of the maximum stimulus of the pain humans might have perceived as per different reports, as per different studies. So that was all about the detailed discussion about all these options A, B, C, D. Coming back to our question, what we have had, this is now coming to the first option. It primarily inhibits the noradrenaline degrading enzyme. If we were talking about this option number C, which was aspirin, that was not true. There are antidepressants which will be degrading noradrenaline degrading enzymes, which will be inhibiting noradrenaline degrading enzymes. Aspirin is not among those. It inhibits the synthesis of prostaglandin. True. We have just seen that COX-2 inhibitors, COX-2 basically cyclooxygenase, are basically responsible for conversion of arachidonic acid into prostaglandin. And if this prostaglandin is not synthesized, then pain can be eliminated. And that cyclooxygenase, that enzyme, is inhibited by the use of aspirin. So that was the correct option. Is it a narcotic drug? We have seen it is not. We have seen that narcotics are the morphine, heroin, codeine, etc. aspirin is not the narcotic one, and it is orthoacetyl benzoic acid. It is not, rather than acetyl, had it been orthoacetoxy benzoic acid, this would possibly have been. As such, when we are saying orthoacetyl benzoic acid, it is not, because orthoacetyl benzoic acid would be looking like, here we are having COCH3 as we have talked earlier, and this is going to be C-double-OH. This is the meaning of ortho. This is not the aspirin. So that is all in this discussion. I hope this is going to be the correct option, as option number B. I hope this was useful, and we have browsed through a lot of concepts, through a lot of discussions related with the mechanisms in the organic reactions as well as in chemistry everyday life. Thank you for being here, and if you are seeing this channel for the very first time, I would like to request you to stay tuned, and if you want to get updated, please like, subscribe, share and comment on this on this video, which will give me energy, positive feedback to do more such videos in future. Thank you. Bye bye. Take care. Stay safe.